Hello viewers, welcome to MAGESH chemistry classes. In this presentation, we are going to discuss CSIR Net TNSET 2024 TRB Assistant Professors Physical Chemistry, Topic 1, that is Quantum Chemistry. In quantum chemistry, the syllabus is the basic principle of quantum mechanics, postulates, operator algebra, solvable system, particle linear empty box, harmonic oscillator, hydrogen atom, shape of orbitals, orbital and spin angular momenta, and tunnel. In this presentation, we will discuss about operator algebra, Hermitian operator. In the previous video, we have discussed the properties of operator and commutator. This video consists of Hermitian operator, properties of Hermitian operator, and some of the important operators are whether it is Hermitian or not. We have discussed some of the MCQs. Finally, we end with previous year questions. That is CSIR net and set questions. Let us move into the theory part. What is the condition for Hermitian operator? Hermitian operator condition is explained by the two ways. One is the operator is said to be Hermitian. The wave function is equal to the interchange, that is. So this is a condition for Hermitian operator. This is a wave function 1 and it is wave function 2. Otherwise, the adjoint of operator is equal to operator A. So these will be explained. So basic conditions for Hermitian operators is this integration of the wave function be like this, or the adjoint of A, that is Hermitian adjoint of A, that is operator A is equal to operator A. We will explain in detail. Then what is Hermitian adjoint? It is a mathematical operation that involves operation transpose and complex conjugate. That is, the adjoint, it is indicated by the symbol trigger. Simply say the adjoint is equal to transpose and complex conjugate. So what is the use of this? The Hermitian adjoint is used to find out whether the operator is Hermitian or not. And it is very important, any operator which is Hermitian in quantum mechanics. So quantum mechanics operators are used, they should be Hermitian. The Hermicity is deducted or explained by the Hermitian adjoint. So regarding the condition, the operator, adjoint of the operator A is equal to operator. This is the condition for Hermitian. Now we discuss about the Hermitian adjoint. The A trigger, so it is the Hermitian adjoint is equal to A, the operator A, then it is called Hermitian. In some cases, the adjoint of the operator A is equal to minus A. So this is said to be anti-Hermitian. In some cases, the A trigger is equal to any other value, it is said to be non-Hermitian. Some of the important things you have to know in this way, that is A, B to operator is the adjoint is equal to, dagger is equal to the reverse, that is B dagger into A dagger. Then the A dagger of dagger, this is equal to A. And the constant and the operator dagger is equal to the conjugate, that is A plus complex and A dagger. Then the two operator A plus B dagger is equal to A dagger plus B dagger. And A dagger of n is equal to a power n tracker. Sixth one, the differentiation d by dx is equal to minus d by dx. And the position is equal to x, and a tracker power minus n is equal to a power minus n tracker. So these are points you have to know. So this Hermitian adjoint is nothing, it is a sum of the transverse and complex conjugate, and these are some of the relations the Hermitian operator case. This Hermitian adjoint is used to find out the hermicity of the operator. Now one question, so that the Px, the momentum operator, is Hermitian or not. Okay. So for Hermitian condition, the adjoint of the operator should be the A. Simply say the operator's adjoint operator is equal to operator. So this is a condition for Hermitian. I replace this Px value, that is minus I h cut d by dx tracker is equal to. So I am going to find out this value is equal to Px. So this is equal to the constant, that is I h cut complex conjugate and d by dx adjoint. The constant is represented in the complex conjugate, that is A star. Okay. So now you find the value I into minus I into star. So what is the complex conjugate value of the minus I? This is equal to plus I. So this will be I h cut d by dx value is minus d by dx. Clear? D by dx is equal to minus d by dx. So this is equal to minus I h cut d by dx. You get the operator. You get the operator away. So Px is the Hermitian. Okay. Now the kinetic energy operator is Hermitian or not. So for that, the Kx tracker should be equal to Kx. The operator adjoint is equal to operator. Now see the Kx value. By putting Kx value, that is equal to minus h cut squared by 2m d squared by dx. So this is a kinetic energy operator. Okay. So this is equal to the constant values are moving away to m, where d by dx to d by dx. Okay. This is equal to minus h cut squared 2m. So this value is not change the constant. Here it is minus d by dx into minus d by dx. Okay, d by dx equal to minus 1. So this is equal to minus h cut squared 2m into d squared by dx. The same values come after kx. So the kx is Hermitian. In this way, the Hermitian adjoint is used to find out the operator is Hermitian or not. Clear? So recall once again. The operator is used to be Hermitian. Then these operators should fulfill this condition. The adjoint of A operator is equal to operator A. Okay. The rules we have to keep in mind it. The A tracker is equal to A Hermitian. A tracker is equal to minus A. It is anti-Hermitian. And A tracker is equal to another value B. It is called a non-Hermitian. Some of the relations are given. Here we have proved that the Px, that is momentum operator, is Hermitian, and the kinetic energy operator is also Hermitian. So these are the operators used in the quantum mechanics. Minimum criteria to use in the quantum mechanics, the operator should be Hermitian. So this is the property of operator, one of the property. Now the Hermitian operator properties. The eigenvalue corresponding to the any Hermitian operator is always real. Suppose you are finding the eigenvalue, that constant value, related to the eigenfunction Hermitian operator. If the operator is Hermitian operator, the eigenfunction value is always real. Let us prove it. Say one operator, that is operator the eigenvalue is A. So this is the eigenvalue. So eigenvalue, eigenfunction in detail we will discuss later. If A is Hermitian, what we will write? That the function of now you put the value of this one. Dot. So A is 1, so this is high star. So A is equal to A star. So the eigenvalue is real. So A is, so what's the property? Eigenvalue corresponding to the Hermitian operator is always real. So this is the first property. And the second one, non-degenerate function corresponding to Hermitian operator is orthogonal. So first property, the eigenfunction obtained from the Hermitian operator is real. Whether any non-degenerate function corresponding to the Hermitian operator is orthogonal. So before entering to explain this second property in detail, first of all we have to know what is non-degenerate function. Suppose a wave function is like this. A is the operator, the wave function, this is equal to the eigenvalue A1, this one. Or the same operator, the eigenfunction, the other eigenfunction, you get the another value. Now, the psi1 and psi2 are the non-degenerate function. Okay. Suppose the operator A star psi1 is equal to A into psi1, and operator operate the second wave function, you get the same eigenvalue we got from the first one. Then it is called, here you get the same eigenvalue, get different eigenvalue. Now you can say it is a generate function, same function. Okay. So this is a non-degenerate function. That is, you have different eigenvalues if the same operators operate in the same different wave function. Clear? So one more example you can say. Suppose we are considering the p orbital, px, py, pz. The total energy operator of the px orbital is equal to E px, and the total energy of the py is equal to the energy py. So all the case the energy is E. So it is a generate function. It is a generate function. So non-degenerate function corresponding to the Hermitian operator. Suppose the non-degenerate functions are operated in the Hermitian, you get the orthogonal. Then what is orthogonal? Functions are vector quantity. It has both scale and direction. Therefore, then its dot product, that is psi1 into psi2, is equal to psi1 into psi2 cos theta. The wave function psi1 into psi2 is equal to 0. When it is 0, if the theta is equal to 90 degree, cos theta is equal to 0. Okay. So this is the condition for the orthogonal. So the two functions are orthogonal, then it is historium n integral dou tau is equal to 0. So this is the condition for orthogonal. Let us consider two non-degenerate eigenfunction. The non-degenerate eigenfunction, one is psi m and psi n, two non-degenerate functions. So their corresponding eigenvalues are am and an. The operator is A. So you get A operator using the psi m, you get the eigenvalue A1, am, psi m. Similarly, the operator n is equal to an psi n. So these are the two non-degenerate wave function. If the operator is Hermitian, you can write psi star m operator psi n dot tau is equal to psi n psi n dot tau. By putting the corresponding value psi star instead of a psi n, you can write an psi n dot tau. In this case, psi n, a star psi m, you can put a power m and this one. Okay. Here the a n is taken out, psi star n dot t. Here the a star is taken out, psi n psi star m dot tau. A n minus a m is equal to here the a n minus a m star, that is the eigenvalue, is not equal. Therefore, psi star m psi star n dot is equal to 0. Okay. So a n minus a star m is not equal to 0. So this is a condition for orthogonal. So this should be 0 in this equation. So what is the second property? The non-degenerate wave function corresponding to the Hermitian operator is orthogonal. So what is non-degenerate function? We have to know. Then what is the condition for orthogonality? So non-degenerate function corresponding to Hermitian operators are orthogonal. The third one, the real operator with multiplication as operation is always Hermitian. The real operator with multiplication. We have studied two multiplication operators. One is the position operator and the potential operator. The operation is multiplication. Therefore, the two operation multiplications of these two are the Hermitian also. Let us take the position operator. Hermitian condition is psi star and position operator and the wave function dot tau is equal to, the operation is changed, so it is psi x star psi star dot tau. So this is equal to, you can write it is psi star x psi. Okay, dot. So operator with multiplication as operation, it is always Hermitian. The multiplication of two commutative Hermitian operator is Hermitian. If the two operators are Hermitian operator and they are commutative themselves, then the multiplication of the two operators are Hermitian. The commutator of two Hermitian operator. See, if the operator A is Hermitian, B is Hermitian, then their commutation is said to be anti-Hermitian, the negative one. Addition and subtraction of two Hermitian operator is Hermitian. Okay, see, these are some of the properties. We will discuss these properties in the problem. Next, move on to the sum of the MCQs. The Hermitian conjugate operator d by dx is. So this is a question from CSIR net June 2011. Hermitian operator of d by dx is. It's a direct one. Tracker is equal to minus d by dx. So the answer is A. Next one. An operator A is defined as A is equal to minus d by dx plus x. Which one of the following statement is true? A is the Hermitian operator. Whether it is Hermitian or not, we have to check. D by dx plus x. To find out the Hermitian, the operator Tracker should be operator. So to find this value, minus d by dx x is equal to what? It is d by dx Tracker plus x Tracker. this is equal to d by dx minus will be plus, and this is x. So it is inverse of this one, so it is anti-Hermitian. Then come to option B. Both A dragger and A dragger into A are Hermitian. A into A dragger is Hermitian or not. So you have to find A into A dragger of dragger is equal to A dragger of dragger into A dragger. The formula is A into B dragger is equal to B dragger into A dragger. What is A dragger? It is minus df dx dragger into A dragger is equal to d by dx of dragger. This is equal to d by dx minus d by dx plus x, here it is plus x, plus x plus x. So A into A dragger is equal to Hermitian. Now we check A dragger A is equal to, simply it is A dragger into A dragger of, so what is A dragger? Minus d by dx plus x dragger into A dragger is equal to d by dx plus dragger. So this is equal to d by dx plus x, and this is equal to minus d by dx plus x. So it is Hermitian. So A into A plus and A plus into A are Hermitian. Correct statement. A dagger is an anti-Hermitian operator. First statement you can find that A plus is a Hermitian, but A dragger and A dragger is Hermitian, but A dragger is anti-Hermitian. So it is also a Hermitian. Wrong statement. Our answer is B. Next question. Identify which of the following operators are not Hermitian. This is a question from CSIR net, December 2011. To find out the Hermitian, you have to apply the Hermitian adjoint. The first one, the option A, that is the adjoint of the operator is equal to operator. So you find out the adjoint. Hi d by dx adjoint is equal to, take out the constant, so it's a complex conjugate, and d by dx. So this is equal to I dagger is equal to minus I. So this is equal to h, constant not change, minus I. It is minus d by dx. D by dx drag is equal to minus d by dx. So this is equal to h by I d by dx. Okay. So operator dragger is equal to operator. So this is Hermitian. Then next one, option B, I d squared by dx squared. Dragger should be I d squared by dx squared. To find I complex conjugate, and this is d by dx dragger d by dx. So I complex conjugate I is equal to minus I, and this is minus of I d squared by dx squared. So the dragger of the Hermitian adjoint is not equal to the operator. So this is not Hermitian. So it is anti-Hermitian. Okay. So your answer is B. This way you can find out that here it will be d squared dx squared. You can write it is d by dx of minus into minus d by dx. So it will be d square, it is Hermitian, and x square. X square also, d in this case x square, it is x dagger into x dagger. So this is equal to x into x is equal to x square. The operator comes. So it is also a Hermitian. So in this way, the Hermitian adjoint is used to find out the operator whether it is Hermitian or not. Your answer is B. It is anti-Hermitian. Question number 5. For any operator, a trigger, the incorrect statement is. You have to check one by one. This is a question from June 2012. A dot A trigger is Hermitian or not. To find out, the concept is operator trigger is equal to operator. So you have to check out. First one is A into A trigger, it is Hermitian adjoint should be operator, is equal to, using formula, so this is B trigger of trigger into A trigger. So this is equal to A trigger of trigger is equal to A trigger. So the operator comes back, it is Hermitian. Okay, it is correct statement. Finding B, A into A trigger plus A trigger into A. Putting adjoint for that, it is A into A dagger of trigger plus A trigger into A trigger. So from the multiplication, this A trigger of trigger into A trigger plus A trigger into A trigger of trigger. So A trigger into trigger is equal to A into A trigger plus this is A trigger, it is A. So the operator comes back. So it is Hermitian. Okay. Regarding C, we want to see A plus and A trigger is Hermitian. How to find adjoint for this. So this is equal to A trigger plus A trigger of trigger. So this is equal to A trigger is equal to A trigger plus it is A. So A trigger plus A. Okay, it is also a Hermitian. Then D, A minus A trigger. So this is equal to A trigger minus of A trigger of trigger. Okay. So this is A trigger minus A. So the operator now comes back. So A minus A trigger is given. Operator. Here A trigger minus A trigger minus A. So it is anti-Hermitian. So the answer is D. Next one, if A and B are non-commuting Hermitian operators, all the eigenvalues the operator given by the commutator AB. If the operators are commuting Hermitian operator, the eigenvalues are real. The operators given are non-commuting, so it is imaginary. Your answer is C. It is given in the properties of Hermitian operator. We can discuss earlier. The commutator of the multiplication of two commutative Hermitian operator is Hermitian, and the commutator of two Hermitian operator is anti-Hermitian. The real operator with multiplication of suboptimal is Hermitian, and in the first property we have discussed the eigenvalue of corresponding Hermitian operator is always real. Non-commutating operator, you get the imaginary values. Then some of the practice questions are given. What property defines a Hermitian operator in quantum mechanics? Eigenvalues are real, eigenvalues are imaginary, and it commutes with all other operators. It always yields positive outcomes. Which of the following operators is Hermitian? The momentum operator, position operator, kinetic energy operator, angular momentum operator. Which one is the Hermitian? And third one, if operator A is Hermitian, what is true about its eigenfunctions? Then fourth one, which property ensures that the expectation value of physical observable is real for quantum system? So answer for this practice questions I have given in the description box. You can do and refer your answers in the description box. Okay viewers, this is the end of our presentation. Thank you for watching this video.